Amplifiers are designed to make signals stronger. But there's a problem. They don't just amplify the signal. They also generate their own noise. So why does an amplifier add noise instead of simply increasing the signal? In the previous lesson, we learned that the first amplifier in an RF receiver has the greatest influence on the overall noise figure. This is why low-noise amplifiers are placed immediately after the antenna to preserve receiver sensitivity. However, even the best low-noise amplifier cannot avoid generating noise. Every transistor, resistor, and semiconductor junction inside the amplifier contributes small random fluctuations that become part of the amplified output. This raises an important engineering question. Why do amplifiers generate noise, and what determines whether an amplifier is considered low noise or high noise? Amplifier noise refers to the unwanted electrical noise generated internally by the components that make up an amplifier. This internally generated noise is added to the desired input signal and reduces the signal-to-noise ratio at the output. Several physical mechanisms contribute to amplifier noise. Thermal noise is generated by resistive elements. Shot noise appears in semiconductor junctions carrying current, and flicker noise becomes important at low frequencies. Together, these noise sources determine the amplifier's overall noise figure. Because every amplifier introduces some additional noise, the objective of RF design is not to eliminate amplifier noise completely, but to minimize it while still achieving the required gain, bandwidth, and stability. Intuitively, imagine using a microphone to amplify someone's voice. The microphone makes the voice louder, but it also amplifies background hiss and introduces a small amount of electronic hiss of its own. Even with no one speaking, you may still hear that faint noise. RF amplifiers behave in exactly the same way. Physically, consider a transistor inside a low-noise amplifier. As electrons move through the semiconductor device, thermal motion, charge fluctuations, and material imperfections generate random electrical variations. These fluctuations are amplified together with the desired RF signal and appear at the amplifier output. Mathematically, amplifier performance is commonly described using gain and noise figure together. An amplifier should provide enough gain to strengthen weak signals while maintaining the lowest possible noise figure so that the output SNR remains as high as possible. Noise performance is one of the most critical specifications when selecting RF amplifiers. The first amplifier in a receiver often determines the minimum detectable signal and therefore the maximum communication range of the entire system. RF engineers reduce amplifier noise by selecting low-noise transistors, optimizing bias conditions, minimizing losses before the amplifier, and carefully designing impedance-matching networks. Even small improvements in amplifier noise can significantly improve receiver sensitivity. Whether designing satellite receivers, GPS modules, Wi-Fi equipment, cellular base stations, or radio telescopes, low-noise amplifier design is one of the most important aspects of RF engineering. Understanding amplifier noise helps engineers choose the right components and optimize receiver performance before any signal processing takes place. Once noise has been added by an amplifier, it cannot simply be removed later without affecting the desired signal. A common misconception is that increasing amplifier gain always improves communication performance. In reality, high gain alone is not enough. An amplifier with excessive internal noise may actually reduce receiver sensitivity despite providing strong amplification. In the next lesson, we'll explore noise in receivers and discover how the combined noise from antennas, amplifiers, mixers, filters, and other components determines the overall performance of an RF receiver. In this lesson, we learned that every amplifier generates its own internal noise in addition to amplifying the desired signal. We also saw why designing amplifiers with low noise figure is essential for achieving high receiver sensitivity in RF communication systems. In the next lesson, we'll explore noise in receivers and see how noise from multiple components combines throughout an entire RF receiver. If you found this useful, like the video, subscribe, and follow for the next lesson.